Alright, welcome back to another JavaScript algorithm training camp session. So in this session, we will be tackling the word count algorithm problem. So let's go over the problem and understand the problem completely. So given a rectangular matrix, your task is to find the number of occurrences of word in the rows, columns, and diagonals of a board. So given this board, which is represented by a two-dimensional array, and a word, we have to find the number of occurrences. We have to find the number of occurrences of this word within this board. So for example, SOS, that would be an example of an occurrence. And then if you actually look down here, SOS, that would be an occurrence. So it's almost like, when we were kids, we had those word search puzzles where it gives you, a bunch of letters and you have to literally go through and find or highlight or circle around each word that you can find. Very similar, but the only difference is that there's few assumptions here. The rows, columns, and diagonals. So we don't need to look, if we're starting from this position, for example, we don't need to go top right. We don't need to traverse it up like this. Same thing, if we're starting from here, we don't need to go bottom left. All we need to do is go to the right, find a word. If you can't find it, go to the bottom, find a word. Go to the diagonal in the bottom right. If you can't find it, don't worry about it. So there's only 3 traverses that you can do from a starting position. And in this example, it's basically explaining that, right? Where same thing. So this is 1, this is 2, this is 3. Then you move on to the next one, and then you repeat the same thing. So let's go over this diagram, which is going to make it a little bit more clear exactly what our approach is going to be. Or first of all, in understanding the problem, and then secondly, what our approach is going to be. Okay, so here we have the word search problem, the word count problem. So we're given a matrix of words. We're going to look for SOS. And the assumptions are we're only looking in 3 different directions. So right, bottom, and bottom right. So for example, let's go through this together, step by step. So as you can see, that would be one solution right there. Or that would be another word that we can find. And there's another occurrence right here. So it almost looks like there's 3. However, if you notice, like I mentioned, this is also a valid case in a normal word search puzzle. But as I've mentioned, this is not valid in this problem set because our assumption is we only need to look for the right, bottom, and bottom right diagonal traverses. So for example, in this case, if I start from here, this top S here, I don't need to go to the bottom left. All I need to do is go to the right, bottom, or bottom right, diagonally. So this is not a valid case. Similarly, if we're starting here, or if we're starting at O, let's just say, we don't need to look in both diagonal directions. All I need to look for is right, bottom, and bottom right. So, let's take a look at our approach and how we will approach this algorithm. So this two-dimensional array, we're going to start by looking at an index. So we're going to start a starting position here. For example, is 0, 0. We're going to look at this word, and we're going to fan out to find the word. So we're going to fan out basically the amount, that's the word we're looking for. So in this case, 2, right? So starting position, 1, 2. Because the word is 3 letters, that's all we need to go. We don't need to go any further. So we fan out to the right, we fan out to the bottom right, we fan out to the bottom for a given starting position, and then we essentially count up how many we can find. So in this case, we found 1 on the right, so we found 1, then we found 1 in the diagonal position. SOS is indeed SOS. Found 2. In the bottom, SSS is not equal to SOS, so we don't count that. And once we're done with a certain starting position right here, we're going to move on to the next one. So the next one in the list is the O. Now, as you can see here, the O is not equal to S, right? Which is the first letter we're looking for. So there is no reason to fan out in this case because the letters don't match. The first characters don't match in the string. So there's no reason to fan out, so we're going to move on to the next one. Just to optimize the algorithm just a little bit. So in this case, we're going to move on to the next index, the next starting point, and we're going to fan out. Same thing here, but one thing you'll notice that's different is we can't fan out 2 positions because we don't even have a character here. In that case, these 2 will never match, right? Because there is nothing to fan out to. But the bottom fan, when we fan out to the bottom, indeed you will find a the same word, SOS. In this case, we count 3. And we're gonna do this, we're gonna just keep traversing, right? We're gonna go through, we're gonna go through each index to the left to the right and top to bottom, and then repeat the same steps, and then we're gonna see how many how many words we can find in this matrix of characters. So that's the basic approach of it. Let's get to coding. Okay, so the problem is on the left-hand side here. Just for reference, I'm gonna be working on this JS file here. I have the word count function. The board is passed in, and the word to search for is passed in. The board is represented by a 2-dimensional array right here, and the word to search is right here. I have the console here, just so I can print out stuff or run the program. So yeah, let's get to it. So the first step here would be use a counter. So we're gonna define a count. Let's just define it as an index or an integer for now. So that's going to count how many words we can find within the matrix. Now what we need to first do is iterate the 2-dimensional array. And the easiest way to do that is just do a double loop. So the first would be we're looping through the rows. And within that row, we're gonna then loop through the columns. So that is represented by essentially this double loop here. So we're gonna loop through the row, and then we're gonna loop however many rows there are passed in by the board. Now we're gonna do another loop within that loop, because within each row we need to loop the columns as well. So we're gonna represent columns with C, and then the iterate the number of iteration is essentially the row, however long that row is. So in this case, this is 1, 2, 4. Just gonna loop it 4 times. And we're gonna just increment that. Wait, so at this point, we're basically looping through each starting point. Now, for each starting point, like we mentioned, we're gonna do a fan out algorithm. So let's make a comment. Fan out algo here. So one thing to note, we can add the condition here where we can add the validation where if this first character is not the first character with the word that we're searching, we don't actually need to fan out, right? So let's just optimize this algorithm just a little bit. So board RC, so this would represent the starting position. If this is not equal to the first character in the word, then we don't even need to bother fanning out. So we can just move on to the next starting position. So that taken care of. This is that here. First character is the same starting position. Okay, so just gonna add that comment there. Now let's get to the fun part, the fanning out port. What we're going to do here is fan out the number of positions depending on how long the word is. So given a starting position here, all I need to go is 1, 2. Starting position here, all I need to go is 1, 2. Starting position here, 1, 2. So I'm going to loop the word, and then I'm going to start with 1, and then we're going to iterate that length. So essentially, I'm starting here, I go 1, oops, sorry. I'm starting here, we're going 1, and then 2. So that basically takes care of the fanning out portion, but we need the direction, or this takes care of the number of characters we need to fan out, but we need to fan out in different directions, right? So fan out to the right. Let's take care of this individually. Fan out to the bottom right, diagonal, and we'll just fan out to the bottom. So let's just treat this all independently. So one thing to do here. Now I'm gonna keep track of the words I'm actually constructing when I'm fanning it out independently. So structured, constructed word right. So by default, we're already at the starting position, right? We're already at the starting position, so we know what the first character is for all the words that we're fanning out to. So let's just keep track of this independently, just so it's clear. And then to the bottom. So this is all going to be the same before it begins fanning out. So once it fans out to the bottom, we're essentially going to do this. Constructed word. We're gonna fan out one character on the first loop, and then we're going to add that character to the string that we're keeping track of. Essentially, let's just do a concat, and then we're gonna add the character column plus W. So what does this mean? Essentially, we're keeping the same row here, but we're looking at the character that's one character to the right of the starting position. That's what C plus W here is indicating. So one position to the right of the starting point. And then we're constructing that word. So at this point, it will just construct SO if we're fanning out one character. Now, fan out to the bottom right diagonal is similar. But instead of in the column we're adding it to the row. Right diagonal. No, okay, so we're adding it to both, right? We're traversing one row down, and we're traversing one column to the right. In this case, we start here, one column down, sorry, one row down, and then one column to the right. And that's what this is representing. Same thing with to the bottom. We're going to, in this case, just move one character to the bottom, which is represented by row plus 1. So here you have it. At this point, you'll see what's going on, right? So we loop through, and we're constructing this word by fanning out either to the right, the bottom right. Oh, here's an error. So replace these. We're constructing the word to the right, bottom right, and to the bottom. And once we loop through the entire word, then we can compare if the constructed word is indeed equal to the word that we're searching for, SOS. And if it is indeed the case, we're going to add to the count. Once that's done for a certain starting position, we're going to loop through to the next starting position, this loop. So we're gonna keep going. 1, 2, 3, 4. 1, 2, 3, So let's just add actually some validation here. So most of the time, sometimes this will not be found. So for example, if our starting position is at the end here, to the right, there is no character. So we'll add that validation. This is just like a catch-all validation here. So we're going to see if there's characters to the right. If there's enough characters to the right. If there isn't, then we're not going to run this at all. We don't need to because there's no characters to append to. So that looks like word.length. So column, we're going to move to the right the number of positions depending on the word length. And if there is a character, then we can construct that new word. But if there isn't, in the case that we're starting here, we move one, it's undefined, it's null, so it's not going to actually do anything here. So this string is always just gonna be the same than what it started with. And we're gonna add that validation logic in here as well, just for good measure. But now, instead of the right, we're validating the rows because we're fanning out. Which one is it? Okay, we're fanning out to the bottom right. Okay, let me actually make this order makes sense. So if board row, and then we're gonna move the number of positions to the bottom, and this is represented by this length. This one. So we're essentially moving two positions down, right? So here, for example, if our starting position here, we'll go 1, 2. We're going to continue on with that. But for example, if we're starting here, there isn't a character. So it's not going to even run this logic. Okay, now let's take care of the diagonal case. Make sure the syntax is correct. Now let's take care of the diagonal, which is a combination of both, right? So in that case, we're going to check the rows. If there's any characters that we can indeed end. So word.length 1. But not only that, we have to check if there's a character to the right as well. Essentially, we're moving here. We're moving bottom, then right. That's the next character. Bottom, and then right. And then this would be the character. So if there is no character to the row, run it, and we're gonna move this R plus. Need to close it. And we need to add the same logic. Right traverse. Wait. Okay, there we go. Okay. So essentially, the diagonal check is combining both the right and bottom. So there needs to be a character. So for example, if I started here, there is nothing to the right and bottom. There is no character here. So there is no word that it can construct. There is no traversal that it can make. So it's going to stop fanning out and it's just not going to construct a word. So those are the 3 cases. And we added some validation so it doesn't throw any crazy errors. Now essentially, the algorithm is almost complete. So for a given starting position, now that we've fanned out correctly, and then we constructed these words correctly, we need to see if the constructed word from this fanning out is actually the word that we're looking for. So we can do that by just doing a string comparison. If the constructed, if I can actually type constructed word bottom, if that is equal to the word we're searching for, then literally add to the count. And we're going to repeat this with this. So paste this. So every occurrence it finds, we're just going to add to count. And then the final result of this function is return count. So at this point, this algorithm is indeed complete. So let's kind of walk through what we created. We have a counter that we're going to track how many we find, how many occurrences we find. We're going to do a double loop here to loop through that two-dimensional array. We're going to first check on the first character. If the first character of the starting position is not equal to the word we're looking for, we don't need to do anything. Move on to the next starting position. And we're going to continue. So all of this is not going to run. We're going to continue to the next starting position. But if the first character is indeed the same, what we're going to do is the fanning out logic. We're going to define some variables here so we can keep track of the words that are constructed while we're fanning out. And we're going to track them independently. So the right, bottom, these words are tracked independently. Now we're going to fan out the number of characters depending on what the word's length. This is fanning out to the right side. As you can see, column plus however many words, however many letters we're fanning out. In this case, we're SOS, we would be starting position and then fan out 1, 2. And we're fanning out two positions. Same thing with the bottom, same thing with the diagonal. As you can see here, that represents to the bottom, that represents, oh no, this is incorrect. So this should not be 1, this should be W. It should be however many, whatever the word is. Because the length of the word, there is nothing defined. So it's dynamic. It can be 2 characters, it can be 20 characters, doesn't matter. Same thing here, right? This is a mistake. So we're not adding 1, but we're fanning out the length of the word. So here, this is good to go. So let's actually try running this and see if we get the desired result. So for this, we will get indeed 3. So do a node.index.js, run the code, and we get an error because this is not called index.js, called solution.js. Solution.count is not defined. Okay, so let's take a look at this and see what's going on. Counter. Okay, let's just add counter here. Great. It always never works on the first try. I've yet to get there. Okay, there we go. 3. So indeed, as you can see, we look at the problem. Boom. There we go. No other occurrences of word were counted, so the answer is 3. So we got the correct answer. So we're doing something right here. So let's further validate our algorithm by passing in the second example. Okay. I'll just comment out this. And then let's pass in the square with AAAA. So as the problem defines it, the correct answer is 5. Because there's 1, 2 to the diagonal, 3 the bottom here. Then we move to the second position, and then all we need to do is run the bottom. So that's 4. Then we're gonna move to the next character, which is the second row, and then there's 5 right here. And then we move to the right, and then there's nothing to look for here because there's no characters to the right, bottom, or diagonal. So indeed, the solution is 5. Answer is 5, so let's run this, cross our fingers, and make sure it's working. Oh, there we go, 5. So as you can see, this algorithm is indeed working for this problem here. Let me see if there's anything that we can show. So let's actually print this out. Let's print out what the constructed words are, just so you know it gives an idea of exactly what's going on when we're fanning out. Bottom. And we're gonna print out the diagonal. Copy paste this. Okay. There we go. Okay, so for each fanning out process, it's gonna basically print out what the constructed word is, just so we know exactly what's happening. And over here, I'll just print out the actual starting point, just so we have a reference. So R would be the template literal here, that we can just embed variables. R would be this. Cool. Now let's run this and see what actually what we. Great. So get an A is probably not the best example to see this. Comment this out. Uncomment this. And then run this. Cool. Now let's see what's actually. You see we have a starting position here, right? 0, 0. And then from there, we're constructing the word. So this is, we're moving to the right, construct the word, moving to the bottom, construct the word, moving to the bottom right, construct the word. Now, because the word is longer than that, we're going to repeat the same process. We're going to move to the right, add that character, move to the bottom, add the character, move to the bottom right, and then we're going to add the character. And at this point, because the length is the same as a word, we can compare it now. So we're going to compare, we're going to say, hey, how many SOS can you find? 1, 2. So it counts. 1, 2. Now, we're going to move to the next starting position here. Now, this starting position, because, as I mentioned, because this character O is not equal to S, we don't need to do any fanning out process. It literally just skips that, moves on to the next. It moves on to the next starting point, which would be S in that case. And S, and there we go, it's fanning out. Fans out to the right, there's an S. Or fans out to the bottom, SO, fans out to the bottom right. 0, 2, so 1, 0, 1, 2, yeah. As you can see, actually, where am I? Okay, so here it is. So as you can see, the right side, it's not fanning out to the right. It's staying the same character, right? The reason why is because remember the validation check we added? We checked if there is enough characters that we can construct the word. But in this case, if we started here, there isn't enough characters to the right. There's only one character. So it doesn't actually construct a word anymore. The only direction that the word is constructed is when we're traversing to the bottom here. To the bottom, boom. It's adding that character, adding that character. So this is a character, so add to the count. So that step is being repeated for every single starting point here. Now, as you can see, you know, this is not the most optimized solution, but it is one way to do it. So for example, there are some future optimizations that could be made, right? Like for example, the last row, you don't need to traverse to the bottom at all because you don't have another row. So you can add maybe those checks that could potentially make your algorithm a little bit more efficient. But yeah, there's probably a bunch of ways to add some optimizations here. So let me know what you guys think. You know, try this out. This is a fun problem. Try it out and let me know what your approach is, if it's any different from this approach, and if there's any optimizations you found while you're doing this, you know, just so I know, and then just so we can compare and then we can learn from each other. All right, so there you have it. So that is the word count problem. I hope that was helpful. That was a little bit long, but hope that was helpful for you. And then hope you learned something new. Thank you for checking in. Thank you for tuning in, and see you guys soon. Alright, if you guys enjoyed that video, please like, comment, and subscribe. Like, comment, and subscribe. Like, comment, and subscribe. Wait, how long am I doing this? Like, comment, and subscribe. Like, comment. Okay, I'm done.